Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So in the previous modules, we have introduced the paradigm or the model for MIMO wireless communication system. We have looked at the matrix channel model of a MIMO wireless communication system, and we also looked at the various special cases of a MIMO wireless communication system. Let us now delve deeper into the theory of MIMO communication systems. So today what we are going to discuss is the receiver in a MIMO wireless system. So we are going to focus on MIMO receiver, that is what is the signal processing that has to be carried out at the receiver. In particular, we will look at what is known as the zero forcing or ZF, zero forcing or ZF receiver. Now remember, we have our MIMO system model. Our MIMO system model is given as y bar equals h x bar plus w bar, and let me refresh your memory. Y bar, this is an r cross 1 vector, x bar is the t cross 1 transmit vector, and h is the r cross t transmit channel matrix, w bar is the r cross 1 noise vector, right. And now the question is, at the receiver, how do we recover this transmitted vector x bar? So we are observing y bar, that is y bar is the received vector. Now from y bar, how do we recover x bar, that is how do we estimate x bar? This is the problem of reception in the MIMO system, right. So how the question we want to ask is how to recover x bar, how to recover the transmitted symbols, how to recover transmit vector x bar at the receiver. Now that is how to recover x bar from y bar. Now let us look at a simple scenario. If, for instance, let us look at a simple scenario. For this simple scenario, let us assume that r is equal to t. If r is equal to t, remember our matrix H, which is an r cross t matrix, is basically it is a t cross t matrix, or in other words, H is a square matrix if r is equal to t. Therefore, what we are saying is our matrix, that is if r is equal to 3, that is the number of receive antennas is equal to number of transmit antennas, then the matrix H, which is r cross t, is essentially a t cross t matrix since r is equal to t. Therefore, it is a square matrix. Okay. Now therefore, if H is invertible, that is not all square matrices are invertible, some square matrices also need not be invertible, right. So if H is invertible, then, so let us consider if H is invertible, then a simple receiver for this scenario is to use the system of linear equations y bar approximately equal to H times x bar. This is our system of linear equations, that is we are ignoring the noise. So this is our system of linear, this is our system of linear equations, and since H is invertible, I can recover x hat as H inverse of y bar. So this is a simple receiver, x hat is equal to H inverse of y bar. This is our this is our simple receiver structure. If R is equal to 3, that is number of receive antennas is equal to number of transmit antennas. So, what we are saying is basically if R is equal to T, that is the number of receive antennas is equal to number of transmit antennas, then the channel matrix H is a square matrix, and therefore, if H is invertible at the receiver, I can simply perform H inverse of Y, and from H inverse of Y I can obtain X. So, I can use the equation Y is approximately equal to H of X. I can treat this as a system of linear equations, and I can solve for the estimate X hat as X hat equals H inverse of Y. That is the simple MIMO receiver. But remember, as we said, as we qualified, this is not always possible. Why is this not always possible? Because H, even though R is equal to T, that is H is a square matrix, H need not be invertible. Further, the most important and interesting scenario occurs when R is not equal to T, that is when R is greater than T, then the matrix is not a square matrix. So, while we can use this if R equal to T and H is invertible, if R is greater than T, that is strictly greater than T, that is number of receive antennas is strictly greater than number of receive antennas is strictly greater than the number of transmit antennas, then H is not a H is not a square matrix, which basically implies that H, that is inverse of H, does not exist. There is nothing known as an inverse of a non-square matrix. Since H is a non-square matrix, the inverse of H does not exist, and in such a scenario, how do we reconstruct or how do we recover the transmitted symbol vector X from the observed symbol vector Y? For instance, if the number of receive antennas is 3, number of transmit antennas is 2, then the matrix H is a 3 cross 2 matrix. There is nothing like an inverse of a 3 cross 2 matrix, right. So, in this scenario, how do we recover the transmitted symbol vector X from the received symbol vector Y? And that is why we need a special concept, or we need a specialized architecture for this MIMO receiver, which we are going to discuss below. Now, let us look at what is happening when R is greater than T. Let us look at this system of equations. Let us look at Y bar equals H X bar. Now, H is R cross T, which implies this system of equations there are basically R equations. And what are the unknowns? The unknowns are basically the elements of the vector X. So, there are T unknown quantities. So, basically R greater than T, if R is greater than T, this implies that the number of equations is greater than the number of equations is greater than the number of unknowns. Therefore, this is an inconsistent system of equations. That is, we have a scenario where we have more equations than unknowns. Therefore, we cannot exactly solve for this vector x from this system of linear equations. Therefore, what is the best that we can do in this scenario? The best that we can do in this scenario is the following. Since we cannot exactly solve for x, what we can do is we can denote this error as y bar minus hx, and the best we can do, that is to minimize the error, minimize the norm of error square, which is basically minimizing y minus h x bar square. That is, what do we want to do? We want to find the x bar such that the error is minimized, that is such that norm y bar minus h x bar square is minimized. Okay. So, what we want to do, we want to find x bar such that norm y bar minus h x bar square, norm y bar minus h x bar square is minimized. And therefore, now you can look at this structure. The structure of this problem is such that it is a square, of the norm, and we are minimizing this square. This is also known as the least squares. This is known as a least squares problem. This is also abbreviated as the LS. This minimization of norm y minus h x bar square is also known as a least squares problem, or it is also known abbreviated as the LS problem. And therefore, we have to find the minimum of this least squares cost function, which is norm y bar minus h x bar square. And how do you find the minimum of a given cost function? To find the minimum of a given cost function, we have to differentiate it and set it equal to 0 and find that x, where is it equal to 0, where it is equal to 0, that gives the minimum, isn't it? So, we have to differentiate it and set it equal to 0. The only problem here is that x is a vector, that is, we have a vector x bar. So, we have to differentiate it with respect to a vector. So, therefore, to find the minimum, we have to differentiate and set equal to 0. However, x bar is a vector. Remember, more specifically, x bar is a t cross 1 transmit vector. Therefore, we have to differentiate with respect to the vector. Therefore, we have to differentiate with respect to a vector x bar, which means we need the concept of what is known as a vector Many of you must be familiar with the scalar derivative. So, we need now the concept of a vector derivative, since we need to differentiate with respect to the vector x bar, which is a t dimensional vector. And this vector derivative can be defined as follows. Consider a function f of the vector x. So, this is any function, this is a function of vector x bar. function of vector x bar, let us say I have f of x bar which is a function of vector x bar, its derivative with respect to x bar is simply defined as the derivative of this function with respect to every element of the vector x bar. So, this is dou f by dou x1, dou f by dou x2, so on and so forth, dou f by dou x. So, this is simply differentiate with respect to every element of x. So, let us say I have a function f which is a function of the vector x bar, its derivative with respect to x bar is basically differentiate f with respect to every element of the vector x, and therefore, it will be a t dimensional vector. Okay. So, what is the derivative? That is differentiate f with respect to every element of x bar, that is the vector dou f by dou x1, dou f by dou x2, so on dou f by dou x t. Okay. That is the definition of the vector derivative of the function f of x bar. Now, let us look at a simple example to understand this. For example, let us consider this simple example which is c bar transpose x bar, which is the row vector c1 c2 times ct times x1 x2 xt, which is basically equal to c1 x1 plus c2 x2 plus so on until ct xt. Now, if you look at this, let us look at this, c bar transpose x bar equals c1 x1 plus c2 x2 plus ct xt. If I differentiate this with respect to, and let us say this is my f of x, so my f of x bar equals c bar transpose x bar. If I differentiate c bar transpose x bar with respect to x1, I can observe that it is the derivative of this summation with respect to x1, which is equal to c1. Similarly, derivative of c bar transpose x bar with respect to x2 is equal to c2, so on and so forth, derivative of c bar transpose x bar with respect to xt is equal to ct. And therefore, I can now write the vector derivative of c bar transpose x bar with respect to x bar as basically c1 c2 ct, which is equal to c bar. So, if I have a function f of x bar which is given as c bar transpose times x bar, the derivative of this function with respect to x bar is simply the vector c bar, right. This is the definition of the vector derivative. Similarly, let us look at another aspect. Now, we know that c bar transpose x bar is equal to c bar transpose x bar is equal to x bar transpose c bar. Therefore, the derivative of c bar transpose x bar with respect to x bar is equal to the derivative of x bar transpose c bar with respect to x bar, which is basically again c bar. Okay. Now, let us look at another interesting function. Let us look at what is known as a quadratic form, that is x bar p x bar, where P equals P transpose, that is P is a symmetric matrix, that is this is also known as a quadratic form. This is our f of x bar. Now, to differentiate this with respect to x bar, I am going to use the product rule. So, I am going to write this as the derivative of x bar transpose p x bar. So, I will consider this as my vector c bar with respect to x bar plus the derivative of x bar transpose p into x bar. I will consider this as c bar. Here I am using the product rule, derivative of f of x into g of x, that is derivative of f of x into g of x plus f of x into the derivative of g of x, which is equal to basically derivative of x bar transpose p x bar with respect to x bar is basically, as we have seen, derivative of x bar transpose c bar with respect to x bar is c bar, which is p x bar, plus derivative of c bar transpose x bar with respect to x bar is c bar. So, this is x bar transpose p whole transpose, which is basically p x bar plus p transpose x bar, and since we have p equals p transpose, this is twice p x bar. Okay. So, the derivative of x bar transpose p x bar with respect to x bar equals twice p x bar. Okay. So, that these are the two results we have for the vector derivative, alright, where we are differentiating with respect to the vector x bar. Now, let us go back to our cost function, that is y bar minus h x bar square, which we are originally concerned with, and now let us differentiate this with respect to h bar. So, our original cost function, least squares cost function or LS cost function, that is f of x bar equals norm of y minus h x bar square, which is basically equal to norm of a vector square is vector transpose times itself, which is basically y bar minus h x bar transpose y bar minus h x bar, which is equal to y bar transpose minus h x bar transpose y bar, I am sorry, h x transpose is x bar transpose h transpose y bar minus h x bar, which is equal to y bar transpose y bar minus x bar transpose h transpose y bar minus y bar transpose h x bar plus x bar transpose h transpose h x bar. Now, look at these two quantities, x bar transpose h transpose y bar and y bar transpose h x bar. These two quantities are the transpose of each other. So, these two are equal. So, this is basically y bar transpose y bar minus twice x bar transpose h y bar plus x bar transpose h transpose h x bar. Therefore, I can write y bar minus h x bar norm square as y bar transpose y bar minus twice x bar transpose h x bar transpose h transpose y bar plus twice, not twice, plus simply x bar transpose h transpose h x bar. Now, this is my, well, of course, this is my f of x bar. Now, differentiating this f of x bar with respect to x bar, I have, of course, derivative of y transpose y with respect to x bar is 0 equals 0 minus twice derivative of x bar transpose c bar is c bar here is h transpose y bar plus Derivative of x bar transpose p x bar is twice p x bar, which is twice h transpose h x bar. I have now differentiated this, I have to set it equal to 0 to find the minimum. Therefore, I have twice h transpose y bar equals h transpose h x bar, which means the estimate h hat is equal to h transpose h inverse h transpose y bar. Therefore, what we have obtained after this procedure, what we have obtained is basically the fact that the estimate x hat, which minimizes the square, of the error, that is the least squares cost function y bar minus h x bar norm whole square, is x hat equals h transpose h inverse times h transpose into y bar, which is also known as the least square solution, which is also basically known as the zero forcing MIMO receiver. This is basically our zero forcing MIMO receiver. So, therefore, we have our x hat is equal to h transpose h inverse h transpose y bar, and this is the zero forcing receiver and I will make a small modification to this. If the channel matrix H is complex, then x hat is going to be, I am going to simply replace the transpose by Hermitian, H Hermitian H inverse H Hermitian y bar, and this is the MIMO zero forcing receiver. This is my MIMO zero forcing receiver, also known as the ZF receiver. This is the MIMO zero forcing receiver. And you can see this quantity, let us take a look at this quantity, let us take a look at H Hermitian H inverse. Now, if H is R cross T, H Hermitian is T cross R. So, H Hermitian H is the product of a T cross R matrix and R cross T matrix, it is a T cross T matrix. Therefore, H Hermitian H is a square matrix, right. So, even if H is a non-square matrix with R when R is greater than T, H Hermitian H is a square matrix, correct. So, H Hermitian H can be invertible. Therefore, zero forcing receiver exists even when R is greater than T, because we are not taking the inverse of H, rather we are considering the inverse of H Hermitian H, which exists even for non-square matrices. Therefore, this is a general MIMO receiver, not just for the case where the number of receive antennas is equal to the number of transmit antennas. That is, this is also valid when the number of receive antennas is greater than the number of transmit antennas. Remember, this is the motivation with which we initially set out to find the MIMO receiver. And if you look at this quantity, this matrix H Hermitian H inverse H Hermitian, this is called the pseudo inverse or left inverse of A, left inverse of H. This is called the pseudo inverse of H because if you multiply this by H, I have H Hermitian H inverse H Hermitian times H equals, now look at this, I have an H Hermitian H inverse, I have an H Hermitian H. So, this is equal to the identity, and therefore, this is acting as a left inverse of H therefore, this is a pseudo inverse of H, because H is a non-square matrix, but when I look at this matrix H Hermitian H inverse into H Hermitian, when I multiply this by H, it gives me identity. Therefore, this is acting as an inverse of H, this is a pseudo inverse of H, alright. So, we use the pseudo inverse of H for the MIMO zero forcing receiver. So, for the MIMO zero forcing receiver, we multiply the received vector y on the left by the pseudo inverse of this matrix H, not the inverse of the matrix H, because inverse does not exist if H is not square. We multiply it rather by the pseudo inverse of this matrix H to get the estimate or to get the reconstructed vector x hat in the MIMO system. This is known as the MIMO zero forcing receiver. Alright, and the MIMO zero forcing receiver minimizes this reconstruction error, that is the norm of y bar minus h x bar square, or the norm of the error square. Therefore, it is basically minimizing the least squares cost function. Alright. So, in this module we have seen how to derive, how to construct the MIMO zero forcing receiver in a MIMO wireless communication system. Alright. So, let us stop this module here. Thank you very much.